Hello everyone, thank you for taking the time to join today's webinar. Today we're going to focus on challenges in flare gas metering and emissions qualification. The TÜV-SÜD webinars are sponsored by the UK Government's Department for Science, Innovation and Technology, or DSIT for short. A recorded version of the webinar will be available to you after this broadcast is finished. This will include the Q&A session at the end. We'd love to hear from you, so please submit your questions anytime during the webinar. You'll find the Q&A panel on your screen, and your questions won't be seen by any other attendees. We'll do our best to get through as many of the questions as we can, but if we do run out of time, we will follow up on any unanswered questions by email. My name is John Dodds. I'm a bid manager, and I've spent the last 23 years at TÜV-SÜD working as part of the sales and business development team. As I mentioned, today we're going to be talking about challenges in flare gas metering and emissions qualification. And to guide us through that subject, we have today's presenter, Colin Lightbody. Colin is a principal consultant here at TÜV-SÜD and has worked in the flow measurement industry for 30 years and has worked in field support, marketing, product development, metrology approvals, and as a flow measurement consultant for international energy companies. So, Colin, if you're ready, I'll hand things over to you now.
Thanks very much, John. Thanks for the very kind introduction, and good morning, good afternoon, or good evening to all the people who have logged in. I really appreciate you taking your time to come and listen to this webinar. I'm going to talk a little bit about my employer, TÜV-SÜD, before we start the webinar. TÜV-SÜD have been in operation for more than 150 years, and we have 1,000 locations worldwide. We're basically a testing, inspection and certification company with over 25,000 employees. We are very active in almost any industry sector you care to think of, chemical and process, healthcare and medical devices, manufacturing. I work for the chemical and process part of the National Engineering Laboratory. Now, the National Engineering Laboratory is based in East Kilbride, and we offer a wide variety of services to a wide variety of industries. We have a computational fluid dynamics team, and again, there is a relevance there because they are very heavily involved when it comes to characterizing the performance of flare gas meters. And we have a data analytics and software services team, and again, there is relevance to today's presentation because they are also involved in developing solutions to help with flare gas metering and emissions quantification. And we also have a very well-established and very capable environmental services team who are mainly involved with things like stack emissions testing, produced water testing, and as I mentioned, flare gas optimization, but many, many other things. Please visit our website for more details. I think it's fair to say that historically, though, we've been known for our contribution at the National Engineering Laboratory, TÜV-SÜD NEL. We're best known for our contribution to the fluid flow measurement industry. And we have, as such, a wide array of flow calibration facilities. Just outside Glasgow, we have our oil, gas, and water and multi-phase facilities, including the UK's national standard. We are the UK's designated institute for fluid flow measurement. And they were designed and still do serve the needs of the oil and gas sector and the water industry. But like most organisations these days, we are also focused on sustainability and net zero. So we have new facilities for testing, research and calibration on hydrogen flow meters, also CO2 for the CCUS industries. We have a gas calibration facility, and we're in the process of commissioning the world's first primary standard liquid and supercritical phase CO2 calibration rig. So today's webinar, I'm going to talk about what's gas flaring and why flare. Some of you may know this, some of you may not. I'll give a quick overview of what a typical flare gas system looks like, and then I'll talk about the challenges as I see them. Emissions quantification, in my mind, is challenging because of the regulatory challenges, the flow metering challenges, and the combustion challenges. So the first, the sections 3, 4, and 5 are really just about how difficult this can be. But then I'm going to talk about a roadmap to a better future, the things that the industry can do globally to make emissions quantification better and flare metering better. And then I'm going to talk about tooth-sud flare sure, literally just a slide at the end to talk about the work that my colleagues have done that I am extremely impressed with to help industry overcome these challenges and to bring about better flare metering and better emissions quantification, and that's called tooth-sud flare sure. I'll finish off before the Q&A, and hopefully, as John said, please send in your questions by talking about a couple of events that tooth-sud are having later on in the year. And I hope you can come and join us at these events. So what is gas flaring and why do we flare? Well, we probably mostly know that it's the burning of natural gas that's associated with extracting hydrocarbons. It is as old as hydrocarbon extraction itself. It's been going on for decades or centuries, depending on how far you want to look back. And it's done for several reasons. You know, economic. It may be that you are in a remote FPSO and you don't have anywhere to put the gas. You don't have a pipeline network like we do in the North Sea, for example. Or it could be that you're unable to re-inject that gas back into the reservoir for geological reasons, which I won't pretend to understand. And safety, of course, you know, primarily gas flares, natural gas flares are safety devices. If something goes wrong, as it sometimes does, we have to get rid of the pressurized hydrocarbons safely and quickly. And for me, as a person who spent many years offshore, while we're developing these emissions reduction plans, we can never lose sight of the fact that there are men and women working on these platforms 24/7, and it's a safety device for them primarily. So yes, we have to reduce emissions. Yes, we have to quantify them better, but we must never lose sight of the fact that this is there to keep workers safe primarily. Regardless of that, it is undeniably wasteful and damaging. Burning natural gas offshore or in a refinery that could be used to power a power station or to heat people's homes is wasteful and it is damaging. If I look at the 2023 World Bank Global Gas Flaring Tracker, 357 million tonnes of CO2 equivalents were released in 2023. 42 million tonnes CO2 equivalent was in the form of methane. And we'll find out shortly why that's really not a good thing. Now, it's maybe worth pointing out that there are different kinds of flaring. And here I have a couple of examples from the NSTA, the North Sea Transition Authority, one of the regulators in my home country. And they have aligned their flaring categories with the World Bank Zero Routine Flaring Initiative. So we have routine flaring, category A, and that's something like, you know, gas disposal on facilities with no export route. You don't have a pipeline, so you have to burn it. And the World Bank's trying to eliminate that by 2030. And it's maybe worth pointing out that if I want to eliminate routine flaring on an installation that has no gas pipeline, well, reductions were probably going to require very expensive facility modifications, you know, building a 100-mile pipeline to take the gas somewhere else, or building a tieback to take it to a nearby platform. So that's expensive, that's time-consuming and costly. We also have category B flaring, non-routine flaring. For example, a planned blowdown. You know, we need to do some work on a generator or a compressor, so we We need to plan that and evacuate the hydrocarbons. And in these cases, reductions in flaring and venting can usually be achieved through operational changes, making your operation more efficient, or optimizing your operations so that you have to do this non-routine flaring less often, and that of course reduces your emissions. And in category C, the most important one in my opinion is safety flaring. And that's an example there, gas disposed of during emergency depressurization events. We need to get the installation safe, and there's not really much we can do about that other than reducing the frequency of emergency depressurization events. So 3 categories of flaring. So what does a typical flare gas system look like? We normally have a liquid knockout drum, and that's basically there to remove condensed and entrained liquids from the flare gas. We also normally have a flashback seal drum, and again that's there to try and make sure that there's no liquids coming back, or no hydrocarbons coming back into the process. And we have a flashback prevention section. So these 3 components here are all designed to ensure that flaring and venting is one-way traffic, that it's hydrocarbons to the atmosphere and never hydrocarbons and oxygen back into the process. But we also have a flare gas meter. In over 90% of cases, if we have a meter, it's an ultrasonic gas flow meter designed specifically for flare gas use. And we also have a flare tip. And this is not just a piece of pipe. These are very complex. They have designs that are highly engineered. And if we want to measure flow rates and combustion efficiencies properly, we need an understanding of these components, the meter and the tip. The tip primarily is there to increase the combustion efficiency by improving flame stability. And if you've been offshore or in a refinery or onshore at an exploration site, yeah, reducing noise. These things are very, very noisy. So if I do want to, measure flare gas properly and quantify emissions properly, which we all do, we're being forced to do that by government regulations. We're voluntarily doing that because of initiatives. I need a detailed understanding of how the tip and the meter perform. The challenge here is that the performance parameters are not static. So that's things like flow rate, gas density, gas composition, wind speed, wind direction. These parameters are not static, and everything changes, and pretty much everything changes all the time. The weather is different from one day to the next. The flow rates could be different. It could be very low flow rates one day and then high flow rates the next day. Your composition can change. Your pressure and temperature can change. Okay, so that's a kind of overview of gas flaring. And I'd like now to speak about what is, in my opinion, the first of the challenges. And that's the regulatory landscape. Currently, although it's changing all the time, most current legislation is focused on carbon dioxide emissions. But methane, which makes up the vast majority of natural gas is anywhere between 75% methane and 98% methane. Methane has a far higher global warming potential than carbon dioxide, which is the measure Andy used. Over a 100-year period, methane has been concluded to be 28 times more damaging than CO2 And over a shorter time scale, 20 years or 25 years, I believe, it's 80 times more damaging to the atmosphere than carbon dioxide. It's a far more powerful greenhouse gas. That creates the paradoxical situation where sometimes creating more carbon dioxide is less environmentally damaging. If I can create an extra ton of carbon dioxide, but in that process I remove a ton of methane from my emissions, I've actually done less damage to the environment. Therefore, it makes sense that methane emissions are a very high priority for the future. And the regulations, the guidelines, the standards, and the voluntary initiatives are all evolving to include methane, rightly so. So, when we look at the regulatory landscape, as far as flaring and emissions are concerned, it's complex and it's dynamic. It's changing on an annual basis. There are global initiatives. For example, I mentioned earlier on the World Bank. They have a flaring and methane reduction partnership, which many people are signed up to. It tracks and monitors flaring levels around the world, and it has the goal of eliminating routine flaring for its own sake, if you like, by 2030. And of course, we're in 2026 now. That's not that far away. We have OGMP 2.0, the Oil and Gas Methane Partnership. It's a voluntary partnership. It's a reporting and mitigation program led by the UN, the United Nations. And it's specifically aimed at the oil and gas industry. You know, there are other methane emitters like agriculture, but this is for the oil and gas industry. And its primary goal is to, first of all, improve the accuracy and transparency of emissions reporting. You can't improve something unless you can measure it. And we'll speak about that with my favourite scientist, Lord Kelvin. So it's a measurement-based framework specifically designed for the oil and gas industry. So obviously, you know, getting the measurement right is the absolute underpinning OGMP 2.0. As I mentioned earlier, you know, Lord Kelvin, a famous Scottish scientist, has a couple of great quotes about measurement that are very relevant to OGMP 2.0. And that to measure is to know. If you cannot measure it, you cannot improve it. And that couldn't be more applicable to flaring and emissions than it is to anything else. On the right-hand side of the screen there, you see some of the companies. Over 100 companies have signed up to OGMP 2.0 from all over the world. So there's a lot of desire by operators and gas transporters and refiners all around the world to voluntarily make things better by measuring better and being more transparent. Because only then can you hope to improve the situation. There are more global initiatives, the IOGP, IPECA, and as well as initiatives, there are guidelines. For example, the Energy Institute are currently creating or rewriting HM58 to help industry determine flare quantities from oil and gas facilities. And as well as guidelines and initiatives, there are flow measurement standards. Work is going on at both national level, for example, BSI here in the UK, and international level, ISO and API in America, to create and update flaring standards to assist industry. A good indicator for me on the importance of flaring is that the ISO organization is creating a brand new document, ISO 17089-3, that's focused purely on the measurement of flare gas. Then, of course, we have regulators, both national, regional, and international. In the USA, there is the EPA, the Environment Protection Agency. In the EU, we have the European Environmental Agency, for example. And in the UK, we have several regulators, you know, the North Sea Transition Authority, the NSTA, the Environment Agency, and, you know, the Scottish Environment Protection Agency, OPRED, and that's part of the Department for Energy Security and Net Zero, and they're all involved with writing and improving and enforcing regulations, all aimed at reducing emissions of greenhouse gases. So for me, the first challenge in flare gas metering and emissions quantification is the regulatory landscape, because it's really complicated and it's really dynamic. Okay, the next challenge for me as to why flare gas metering is so challenging, well, that's the actual flow measurement itself. As I mentioned, most flares have a meter. It's usually an ultrasonic meter, sometimes a thermal mass meter. And generally speaking, regulators and operators are looking for an uncertainty, an accuracy, if you like, if you're not a metrologist, of 7.5%, or even less than that, sometimes 5%, on the mass flow rate or the standard volume flow rate. More and more often now, we need a technically defensible flow rate, something that can be verified independently. And for most operators, they're likely to be using a large diameter pipeline with a single or dual path ultrasonic meter. It probably wasn't flow calibrated because it can't be flow calibrated. You know, where do you take a 36-inch flare line with complex inlet pipe geometry? Where do you take that if you want to calibrate it between 0.05 and 100 meters per second? The facilities don't exist. It may have no measured spool piece, unlike a highly engineered custody transfer ultrasonic meter. It may just have transducers welded into the pipeline. Nothing inherently wrong with that, but you don't have the same control or confidence in your geometry. And more than likely, it's got a complex inlet piping geometry. And that will give rise to significant installation effect biases. The flow will not be traveling through the pipe in an ideal manner. So the challenges just keep coming for flow measurement. It's probably operating with no live gas composition information available, unlike a gas export system, which will more than likely have a very accurate and very up-to-date composition coming from a gas analyzer. That's not very often the case for flares. It's a sample that was taken 3 years ago, or the operator uses the gas export sample or the fuel gas composition. So these all increase the uncertainty. It's almost certainly running a proprietary calculation. You know, most flare gas manufacturers, and I'm, you know, familiar and I know a lot of these people, they're friends of mine, they almost always run a proprietary calculation, and I don't have an issue with that. Intellectual property is, you know, important. Why should they give away information that they researched and developed? But there is an issue there that I'll talk about as the landscape changes. And in many cases, you know, for the older systems, the 20-year-old, 25-year-old, 30-year-old flares, we're talking pre-digital communications for a lot of these installations. So they're probably using a 4 to 20 milliamp output and an analog input at the DCS or the flow computer. And it's probably got a very large range to cover the operating range of the flare. So that's, in that case, they're a 1,000 to 1 turn down ratio. And possibly, as we move into a low flaring landscape, it's possibly running for the vast majority of the times at very, very low flow rates. And that's a challenge from a measurement perspective. Here's some anonymized data from an actual platform in the North Sea. You can see over 1 year, we looked at the flow velocities from the LP flare and the HP flare. And for the overwhelming majority of the time, the LP flare is running at less than 1 metre per second. And same for the HP flare. For the overwhelming majority of the time, it's running at its very lowest flow rate bucket, 1.6 metre second below. And a lot of these were 0.1 metres per second, 0.05 metres per second. The flare gas is hardly moving through the meter because they're trying to minimise the amount of gas that they flare. Now, from a measurement perspective, that's extremely concerning, extremely challenging. If I look at a typical example here, a typical DCS analog input that has an uncertainty of 0.2% of span, up at 20 or 40 or 60 meters per second, the uncertainties are very low. And if I look at a high quality ultrasonic meter with a stated manufacturer uncertainty of 0.1 meters per second, again, at 20, 40, 60 meters per second, everything's fine, very low uncertainties. If I'm trying to minimize my gas flows, well, let's look at what happens when I zoom into the lower flow velocities. On the left there, you can see that the uncertainty of the analog loop itself becomes significantly larger as the flow rate decreases because it's a percentage of span. So we can see there that anything below 2.6 meters per second and my analog loop uncertainty is already 7.5%. And if I look at the ultrasonic meter, again, a high quality ultrasonic meter with a 0.1 meter per second absolute uncertainty. In this particular case, any flows below 1.3 meters per second, and my absolute uncertainty from the ultrasonic meter is already 7.5%. And if I go lower, they get bigger and bigger exponentially. And remember, I'm only talking here about flow velocity or uncorrected volume flow rate. We've not even mentioned pressure uncertainties, temperature uncertainties, density uncertainties, composition uncertainties that we need for standard or mass flow rate. So low flow is a challenge. We also have installation effects. If I look at a typical flare gas system, the inlet pipework has bends, T-pieces, thermal wells sticking into the line, branches. And from a flow metrology perspective, anything that's not a long, straight piece of pipe is basically an unwanted, undesirable installation effect. Now, typically, the manufacturers will recommend 20 to 30D upstream, but they'll always quite rightly say the more, the better. And they usually recommend something like 5 to 10D downstream, again, quite rightly, because they're knowledgeable people. They'll say the more straight pipe you have, the better. That's because these meters, the ultrasonic meters, they require a fully developed symmetrical flow profile in order for the calculations to be accurate. The calculations assume that developed flow profile, and that's where their uncertainties come from. The question I think the industry should be asking itself, and already is in many cases, is are the recommended installation requirements, are they adequate? Are they fit for purpose? And the work my colleagues have done that I've been party to over the last few years suggests that in many cases they're not adequate. Why is that an issue? Well, if we look at the example here of an out-of-plane bend, a relatively simple installation effect, we can see that depending on where I put my transducers for the ultrasonic meter, I could either overread significantly or underread significantly. And again, bear in mind we're trying to have no biases, no installation effects, and minimal uncertainty with a single path or a dual path meter. We can then move on to proprietary calculations. I mean, again, I fully understand intellectual property, and I have great admiration and respect for the people who have developed these calculations that have allowed the industry to calculate mass and standard volume flow without a live gas composition. It's an incredible piece of work. So proprietary calculations are not bad as of themselves, but in the changing landscape, as we adopt a fiscal mindset for flare metering, there are challenges there. By their very nature, they're extremely difficult to independently verify because you don't have any calculation details. That is the property of the manufacturer. There's rarely any live gas composition knowledge for a flare gas system. So that means that assumptions have to be made about things like molecular weight, compressibility, speed of sound, and also how these all interrelate with each other, because everything, as I mentioned earlier, is very dynamic. Because it's proprietary, there's no clear understanding on how any correction factors are calculated and how they're applied. And what I mean by that is, if you're applying your corrections based on flow velocity, how accurate is your flow velocity? If you have a bias caused by an installation effect, your flow velocity is possibly not representative. If you're using a Reynolds number based correction factor, which seems to be the common sense approach, then how accurate is your Reynolds number? If it's based on assumptions about a gas composition that are untrue, then your viscosity might not be accurate, your density might not be accurate, your velocity, because of installation effects, might not be accurate. So the Reynolds number equation, rho Vd over mu, how accurate is your Reynolds number? And if you don't know how accurate your Reynolds number is, there's a great danger that you're applying the wrong correction factor for any given flow velocity. Now, just to think about that for a minute, if this was a gas export system, you would never get that past a regulator. How do you calculate mass flow? It's a secret. What gas composition do you use? A sample from 2 years ago. These rules that we apply very rightly to gas export systems, we're going to have to adopt that kind of mindset if we are going to make, adopt a fiscal mindset for flare gas metering. So no issue with proprietary calculations whatsoever, but we have to bear it in mind along with the changing landscape and the changing regulatory landscape. So the flow measurement challenges. In summary, low flows are challenging, installation effects are challenging, proprietary calculations are challenging, and then just another subject that's been given a lot of consideration recently. Are we doing routine maintenance that potentially makes things worse? So we do routine maintenance in flare meters, and it generally involves removing the transducers. Transducers can be really quite substantial in length, and we put them back in. Are we absolutely sure that we've put them in exactly the same place? Are we sure that the geometry is exactly as it was before? Well, perhaps it is, but perhaps there's other ways that we can maintain ultrasonic meters using, for example, condition-based maintenance. If we know the speed of sound and we know the signal strength, there's maybe things we can do to let us know that actually there is no need here to do maintenance at this particular time. So for me, consistently obtaining low single figure, traceable and verifiable uncertainties for a typical flare gas meter is extremely challenging. But let's assume just now, let's assume for the moment, sorry, my fire was on, my room like a furnace, that we can get the meter accurate. Let's assume that we have an actual mass, an actual flow rate, a standard volume flow rate, and a mass flow rate that are all low single figure uncertainties, 5%, let's just say. Does that make it easy to quantify emissions now that we have the flow rate spot on, or as good as we can get it? Well, the answer is not really. And that brings me to the third of the challenges as I see them for emissions quantification. and that's combustion. So if you've been in the industry for a long time, it's very clear and very obvious that some flares are a lot better than others. I'm not going to give out any prizes for anyone who's logged in for telling me which one of these flares is suboptimal. The one on the right is clearly not combusting as well as the one on the left. So even if we get the metering right, there's still a lot to consider before we can be confident in our emissions quantification. The combustion challenges. So I'm not a combustion expert here, folks, but as the regulations and guidelines are taking shape, there's two measurands that are becoming more and more to the fore. That's combustion efficiency and methane destruction and removal efficiency. So I'm going to show my lack of knowledge here by reducing this to simple high school chemistry. Combustion efficiency is kind of defined as the percentage conversion of the hydrocarbon components, methane, ethane, propane, pentane, to their end products of combustion. Complete combustion, that's CO2, carbon dioxide and water. No carbon monoxide, nothing else, just the conversion of hydrocarbons to CO2 and water. So, for example, if following my combustion in the flare tip, there are no hydrocarbon molecules, there are no carbon monoxide molecules, everything has been converted to carbon dioxide and water, then the combustion efficiency, the CE of that flare, is deemed to be 100%. There's an example there of a hydrocarbon combining with oxygen and being fully converted to carbon dioxide and water. The second measurand that's coming to the fore is the methane destruction and removal efficiency. The focus on methane because, as we discussed earlier, the global warming potential is so much higher than that for carbon dioxide. And the methane destruction and removal efficiency is the number of molecules removed or destroyed in the flare relative to the number of molecules entering the flare. I'm simplifying this, folks, because I'm a simple man. So, for example, if my flare has 100 methane molecules entering the flare tip, and post-combustion there are only 2 methane molecules, then the methane DRE for that flare is 98%. And there's a simple high school chemistry equation: methane plus oxygen converted completely to CO2 plus water. So CE and DRE are two of the most significant measurands that we're using now for emissions quantification in the oil and gas industry. Now, a lot of assumptions are made about CE and DRE values. Historically, we've used a figure of 98% for CE and DRE. It's widely used, it's widely accepted. Well, where did this come from, this 98%? For a while, I thought it was just flare lore, one of these figures that you could search forever. However, I have some very smart colleagues, and they've pointed out that it's actually some very good research from the US Environment Protection Agency, but it was 40 years ago that this was done. And it basically says that flare efficiencies can be very high, but under certain operating conditions, low efficiency can result. Now, there's some realities for me about CE and DRE. The efficiency of a flare, we saw the image earlier on with 2 flares, one efficient, one inefficient. There's many factors affect the efficiencies. The design of the flare tip, as I mentioned, is not just a piece of pipe, it's a highly engineered, sophisticated piece of metal designed for flare optimization. The exit velocities at the flare tip, it's expecting a certain velocity to be there to optimize combustion. It has an operating range like any other piece of engineering. The wind velocity is very important. And for example, offshore, when all the flares are very close together, even the wind direction can play a part in the efficiency of a flare, because the flame from one is literally blowing into the gas coming out of another. So wind speed and wind direction play a part. Clearly, the process conditions and the gas properties, in particular the calorific value, the density or the calorific value of the gas. And so the question for industry, I believe, is a static figure representative or fit for purpose when it comes to reporting and then trying to reduce emissions? Well, for me, again, the answer is no. A static figure is not fit for purpose, and it's quite easy to demonstrate that. I have an image here of a flare that's been CFD modelled, and at the moment, on a still day, 3 metre per second wind, the combustion efficiency and the destruction and removal efficiency for methane are both very, very close to 100%. If I keep everything the same, except the wind speed, and I have a windy day or even a very stormy day, we can see that significantly impacts the efficiency of the flare. And on the right-hand side example, 97.7%, we're now below the assumed 98%. So sometimes we were way above the 98%, and sometimes we're below the 98%. So I question the validity of a static figure as the guidelines and the regulations become more sophisticated. And of course, what about installations that have a flare gas recovery system, which is great? Great. You want to have a flare gas recovery system to reduce your emissions. But the information the data that my colleagues and I have seen, it means that you're running at ultra low flow velocities, ultra low flow rates. So you hardly get any gas going to the flare. And sometimes, if you're in the North Sea, for example, at this time of year, the wind can be very, very high. So if you look here, again, a wind speed of 0.5 meters per second, but we're looking at an extremely low flow rate. The DRE for methane is 98.7%. But if that's a windy day and you're running at an extremely low flow, something like 0.05 meters per second, right on the limit of what the meter can measure, then our CFD modelling suggests that that's a potentially unsafe situation. You can see there that we have combustion taking place and oxygen ingressing into the flare tip, and that's clearly a very undesirable situation. So that's our simulations. That's what they suggest: combustion inside the flare tip, and nobody in the industry wants to see a situation like that. Now, there are some misreporting risks. We at TÜV think that you're soon going to be paying for methane. That's the way the regulations are going. It's already the case in America with the Inflation Reduction Act, and we think the EU and other world areas are going to follow suit. If you're under-reporting your emissions, well, that's quite clearly a bit naughty. That's a mismeasurement. Will there be large fines on the horizon? Possibly. But what if your efficiencies are greater than 98%? What if you're doing a really good job and you're at 99.6% for your efficiencies? Well, that means you could end up overpaying. And again, that's never a good business model for any operator. We have to remember that, if I increase my methane destruction and removal efficiency from 98 to 99.5%, that's only a 1.5% increase, but it's a 75% reduction in my methane emissions. It's a huge reduction in my methane emissions. So as regulations evolve and as perhaps a price is put on methane, emitted methane, am I missing out on a potential 75% saving? Who knows? Just to look at that graphically, again, this is real flare data. A customer here is obviously, anonymized, but by you looking at a 98% efficiency for the flare and a price for methane that's 28%, 28 times larger than CO2, we can see the reduction for one flare over a year from 1.8 million US dollars to 92,000 US dollars, brought about by increasing their methane DRE from 98% to 99.5%. Now, even for the largest operators in the world, for a single flare, that's a significant saving. So hopefully that made some sense, folks. You know, there are three main areas of challenge as far as I see it: regulatory landscape, the flare measurement itself, the flow measurement, and the combustion challenges. So that's, you know, possibly quite a bleak first section to the webinar. However, there is, I believe, a roadmap to a better future. I believe that. Many others believe that. We're working closely with many organisations and manufacturers and regulators at TÜV SÜD to map out this roadmap. If I've done my presentation well up to now, then hopefully the challenges in metering and quantification are very, very clear. We need to get the meter accurate. And I know that some manufacturers are looking at improving the design of their meters, designing new meters, maybe increasing the number of paths involved to make them more like custody transfer meters. That would be a huge leap forward. You know, if you, for example, had a 4-path meter, the effect of installation effects is dramatically reduced. Getting the CE and DRE values right, and that's maybe by using a more dynamic approach rather than just assuming 98%. And then optimizing the CE and DRE values to minimize emissions. As I mentioned at the very outset, sometimes that would be increasing your CO2 in order to reduce your methane. And then also providing operators and regulators with calculations which can be understood, audited, and verified. We're quite happy to use ISO calculations and AGA calculations and GERG calculations for gas export, and they're all public domain. They can all be independently verified. So why don't we use them for flare gas meters? Nothing against the proprietary calculations, but if I want to verify my emissions reporting, why don't I verify it using auditable and publicly available calculations? So there are things we can do with the meter, with the efficiencies, the combustion efficiencies, and with the calculation for reporting purposes. Now, a lot of work, a lot of people recognize this. So a lot of work is being done all around the world by some very intelligent people, way more intelligent than me, to try and make emissions quantification better. There's a top-down approach, and that's using, you know, in order of height, drones, then planes, then satellites, to look down at the Earth's atmosphere, either from space or locally using a drone on site, and doing some sort of survey to measure the CO2 and the methane coming from flares. There's the bottom-up approach, which is assessing and quantifying emissions at source, and this is the part that I'm involved with, trying to make flare metering better and make emissions quantification better. And just as a matter of interest, OGMP 2.0 regards the gold standard as being able to reconcile top-down and bottom-up measurement, you know, as a way of verifying on an ongoing basis that your emissions quantification is correct, and by default that kind of means your flare metering is correct. Just to be a bit of shameless self-promotion here for my colleagues, we are one of the organisations leading the way. We are by no means the only organisation, but we are one of the organisations. So I'd like to take a few minutes just to explain what we're doing. We have developed a service, using various technologies, using CFD, using software, and we're calling it tooth-sud flare sure. And I just want to explain what it does, but it may or may not be of interest to the people who are listening to me. There are kind of 4 parts to flare sure. We can and have used CFD modelling all the way from the knockout drum to the flare tip over the full expected operating range of the meter, or indeed the full historical operating range of the meter, to model the performance of the meter and model any installation effects. So that allows us to generate correction factors, which can be significant in our experience, 5, 10, 15, 20, 25%. And these correction factors, based on the customer's pipework and the customer's process conditions and the customer's fluids, they can be used to the models can be used to generate correction factors that remove the installation effect biases. Do these models have their own uncertainty? Yes. Do we need to better understand the uncertainty that these models create? Undeniably. But there's certainly a method, a route to improving the flare gas metering challenges. We also offer, as part of tooth-sud flare sure, a flare tip optimization service. And this is, again, based on computational fluid dynamics, but it's taking the customer's flare tip and modeling the performance of that flare tip over all of its expected or historical operating conditions and all the prevailing weather conditions. That's quite easy to get the history of wind and weather in almost every world area now. And what that does is, rather than having a fixed value for CE and DRE, it provides the operator with a dynamic value for CE and DRE, which is based around their weather conditions, their flare tip, their flare meter, and their process conditions. So these are optimization services that we can also combine with traceable calculations. The flare sure product is available on hardware or as a cloud solution, and it uses, for verification purposes, established and transparent calculations like ISO, AGA, and GERG. And it provides live calculations in real time of combustion efficiency and methane destruction and removal efficiency. And we bring all that together, and we say it's intelligent flare management. It's not just measurement now, it's intelligent flare management. So the flare sure product, as opposed to the optimization services, it combines the outputs from the CFD models, the traceable calculations, and live weather data, and the outputs are real-time quantification, real-time flow rate reporting, real-time combustion efficiencies, and methane DRE efficiencies. It has live uncertainties for many of these figures, and it allows the operator to do flare optimization. If an unsafe situation looks likely, the flaring can be changed. If the combustion efficiencies are becoming too low, the flaring can be changed. So we like to think I'm very impressed with the work my colleagues have done. It's really quite astonishing, and we believe it's the right service to produce at the right time for the oil and gas industry worldwide. So in summary, folks, I can see I've got 6 minutes left. My colleagues will be relieved that I'm within schedule. Hopefully this webinar has made it clear, if you didn't already know, and you probably did, that accurate flare metering and accurate emissions quantification has never been more important, and it will continue to increase in importance and relevance as the years go by. I've hopefully made it quite clear that it's really not that easy to get a flare meter accurate, and it's really not that easy to accurately quantify your emissions, whether that be methane, CO2, or CO2 equivalent. There's regulatory complexity and the viability of doing these calculations. There are flow metering challenges. But by regulatory viability, I mean, is it possible to meet a 7.5% uncertainty if you have a flare gas recovery system and you're flowing at 0.1 meters per second? I would say no. I would say in these cases the regulations are not viable, even though the operator's trying to do the right thing, reduce his emissions, reduce his flaring. There's the flow metering challenges, which we spoke about, installation effects, low flows, proprietary calculations. There's the understanding of combustion complexities. It's not just as easy as my flare is 98% efficient. But hopefully I also explained that the improvements are possible. And without trying to be too much of a salesman, my colleagues at TÜV SÜD, we can help improve emissions management. Before I finish, folks, I just want to talk about a couple of upcoming events hosted by my employer, TÜV SÜD. We've been doing this for over 40 years now, all around the world. We have several events this year, but we have two premier events, if you like, the flow measurement workshops. In April, in Abu Dhabi, we are having the ASMEA flow measurement workshop. That's Asia, Middle East and Africa flow measurement workshop. It's in the Radisson Corniche Hotel in Abu Dhabi. 3-day event, really high quality technical program, which will be released within days. And then later in the year in Edinburgh, we have the 44th Global Flow Measurement Workshop, held in Edinburgh for the first time this year. It's previously been in Peebles, Aberdeen and St Andrews. Every second year it's held in Tekna, an amazing event held by our colleagues in Norway, our counterparts in Norway. Great history to the event, world-class papers from experts from all over the world, fantastic networking opportunity, fantastic educational opportunity. The call for abstracts is still open. It's actually not the 30th of January, it's a misprint, it's the end of February, I believe. So if you have any metering related work that you're doing and you want to share that with your peers and come along and learn from your peers, maybe make some new friends, learn a lot, then please feel free to submit an abstract that will be considered for inclusion in the programme. And that's taking place 29th of September to the 1st of October, slightly earlier than historical events, based on feedback for attendees who have children at school. So 2 events, folks. I would encourage you to come along to one or preferably both of these events, Abu Dhabi at the end of April and end of September, beginning of October, for the Global Flow Measurement Workshop in Edinburgh. That's it for me, folks. 11:28. Thank you very much for listening. I'm not actually sure if we've got any questions or not, John, but if we do...
If we're really, really quick, we've got time for a couple, okay? So
Okay.
We'll dive in. Right, okay, first question. How realistic do you think the 2030 target is for zero routine flaring? With 4 years to go, that might be a bit ambitious.
I think it will be, John. And I don't think it's unfair of me to say that it'll split down geopolitical lines. There'll be some countries that are, in some world areas where the push is greater, the desire is greater. There are places like Norway or even global operators like BP who are really pushing for this and will probably manage most of their assets. There are other world areas where I fear that very little progress would be made. So, yeah, I think it's going to vary wildly from location to location. Do I think that there'll be zero routine flaring by 2030? Old cynic that I am, no.
Yeah, I think you're probably right. Okay, listen, we've actually ran out of time. So for those of you that have asked questions and haven't had time to answer them, we will follow those up. So as I mentioned earlier, we will be sending you the on-demand version of this webinar after the event is finished. For the attending the event, you have earned yourself 10% off any TÜV Sud Academy training course if you use the exclusive discount code webinar_10. Keep your eyes peeled for other webinars about this topic, which you'll find on our resource section on our website, www.tuvsud.com/en-gb. Please get in touch with us and let us know if there are any other webinar subjects that you would like us to cover. It's always good to hear exactly what you guys are interested in. Feel free to get in touch with me via the email on screen or send any inquiries to info.uk@tuvsud.com. And on behalf of myself and Colin, thanks for your time and enjoy the rest of your day.
Thank you very much, folks. Really appreciate your time.